Hello students, welcome to the ninth tutorial class on artificial intelligence and fuzzy logic. And this class will be presented by myself, Dr. Sudip Mandal, Assistant Professor of Department of Electronics and Communication Engineering, Jalpaiguri Government Engineering College. So these are the contents that will be discussed one by one. First one is the delta learning rule. In the earlier classes, we have discussed two another learning rule. One is Heavian learning rule, that is the unsupervised type of learning technique, and next one was the perceptual learning rule, that was the supervised learning technique. And in this class, we shall discuss the mathematical formulation of delta learning rule, which is basically a supervised learning technique. And after that, we shall discuss two architecture of neural network. One is Adeline, another is Madeline. Basically, delta learning rule has been applied on these two neural network architecture. So let's start. First one is the delta learning rule. So basically, this learning rule is proposed by Woodrow and Hoff in the year 1960, and it is also called as the least mean squared error, and where the error between input and target output, sorry, error between the calculated output and the target output uh, is minimized during the training process. Okay. And remember, delta learning rule is one of the supervised learning algorithm. And moreover, another point it should be keep in mind that in case of delta learning rule, we consider the continuous activation function like sigmoid function, etc. Okay. So let's see the mathematical formulation. Basically, it is a quite similar approach to the perceptual learning rule, but the difference is in the weight updated formula. So in case of delta learning rule, to update the synaptic weight, the delta rule is given by delta omega I. That means the change in the weight of ith neuron is alpha into xi into ej. Okay. So alpha is the learning rate. Okay, basically it is a constant, and its value is positive in nature. Normally its value is keeping in between point 0.1 to 0.01, like in this range. So it can be varied according to our application. And next one is the xi is the input value from the presynaptic neuron. And next one is the most important part, that is the difference, or ej is the nothing but the difference between target and the calculated output. Okay. So that's why we use the term delta learning. Okay. So based on this value, the weight can be updated. Okay. So uh, the new weight can be given by using the following formula. So when t not equal to y, that means when the target output is not equal to the calculated output, so in that scenario, the new weight will be old weight plus delta omega, and delta omega is nothing but alpha into xi into error. Okay. So xi into ej. Okay. So that is the delta learning rule. When target output is not equal to the calculated output, but when t equal to y, so there will be no change in the weight. Okay. So that is a simple approach. Only the difference is the change in the delta omega, where the error between t and y has been introduced. That's why the term delta learning rule, because by on the basis of the difference between target output and the calculated output, the weight are updated. Okay. Now, this simple delta learning rule has been implemented, or can be implemented, on two different type of architecture of neural network. Those are called as Adeline and Madeline. Okay, so let's see what is the Adeline type of uh, architecture of neural network. So basically, the full form of Adeline is adaptive linear neuron. Okay, so ADA stand for adaptive, LI stand for linear, and NE stand for neuron. Okay. So and it should be remembered that it is also developed by Woodrow and Hobb in 1960. And some important features of the Adeline network can be stated as follows: that it has a bipolar activation function, and it uses the delta learning rule to minimize the mean squared error. That means the difference between the actual output and the desired or target output. And obviously here the weight and the bias are adjustable. Okay, and it should be keep in mind that it is basically a simple simple single single layer perceptron model. Okay, so the basic structure of Adeline is quite similar to the perceptron, having just one another extra feedback. You can see that this one is basically nothing but the perceptron model. Here you can see that x1, x2, xn, and this one is the bias. Okay, and B, W1, W2 up to Wn are the respective weight associated with the bias, and the inputs all are going to the accumulator part, and there you can get the yin xi plus wi. Okay, and it is going through the an activation function, and we get the ultimate y. So that was the basic a simple perceptron model. But here the new part is only that there is an extra feedback path where the difference between target output and the actual output and the calculated output has been calculated. That means here you can see that there is another part or another block where output error can be calculated. You can see that here error has been incorporated. So e equal to t minus yn. Now this value is going to the adaptive algorithm, and based on that algorithm the weight and bias value can be adjusted. Okay, so this is the basically the Adeline model or architecture of Adeline. Okay, so here you can see that the basic structure of Adeline is quite similar to the perceptron, having an extra feedback loop with the help of which the actual output is compared with the desired or target output, and after the comparison on the basis of the training algorithm the weight and the bias will be updated. Clear? So this one is the extra part. This is on the Adeline model or Adeline architecture model. So let's discuss about the Adeline training model. So in case of Adeline training model, we already discussed that we can implement the delta learning rule here. So let's start. So in step one, we should initialize the different weight, like different weight between inputs and the accumulator. So W1, W2, W3, and we should also initialize the bias value, and we should also initialize the learning rate. Okay, so in normal cases, weight and bias should be are initialized to the 0, and learning rate is set to the 1. It is the most simple approach. And next one is the step 2. So continue step 3 to 8 when the stopping condition is not true. Basically, stopping condition that means there may be some kind of tolerance limit of error. Like if error reach beyond the, like for example 10 to the power minus 10, so we should stop. That means we can achieve the our desirable accuracy so far, so we don't want to proceed further iteration. So that may be a stopping condition. That mean moreover the another stopping condition may be the number of iteration or number of epochs that we want to continue. So the stopping condition may be different, like the tolerance limit, or you can say it the number of epochs or number of iteration. So stopping criteria is imposed in the step 2. Next step 3, continue step 4 to 6 for every bipolar training pair. So next we are considering that iteration will be continued up to when all the training pattern or data set are compared, okay, or considered. Okay, now step 4, activate each input as follows. That means all the inputs are as implemented, like x1 equal to s1, x2 equal to s2, like this way. So activate each input as follows for each of the training pattern. So we are considering like first training pattern. So obviously for that case, like s1 s0 sorry s1 s2 s3 are imposed to the x1 x2 x3 respectively. Next we want to calculate the net output after that. So basically, so you are calculating this. Okay, so as per the formula we know that b plus summation from I to n xi wi. Where b is the bias and n is the number of input neurons, so we are calculating the uh, total output. Okay. Now this can be going through the activation function. So activation output of the activation function will be fyn. So that value of the activation function is bipolar already know. So it will be value 1 if yn greater than equal to 0, and it will take the value -1 if yn less than 0. Okay. Now coming to the weight updation part. So adjust the weight as and the bias as per the following rules. So then we should compare the target output with the calculated output. So if y not equal to t, then obviously new weight will be like this way. So new wi new equal to wi old equal to plus alpha into e means t minus yn, that means difference between target and the actual output, into xi. Okay, whereas the in case of b new bias, and the b new will be b old plus alpha into t minus yn. Here you can see that there is no term associated with the xi, because the value of by default value of b or x0 equal to 1, so that's why we are not using the term xi, because it is multiplied by 1. Okay. So this one is the basically the weight updation formula, and this weight updation formula is nothing but the delta learning rule, and it will be implemented if y not equal to t, and if the y equal to 2, there will be obviously no updation take place. Okay. So here t minus 1 is the computed error, and this value is going through the learning algorithm to adjust the weight and bias value. Okay. So step 8 next is the step 8. So this one are basically the test for the stopping condition, which will happen when there is no change in the weight, or the highest weight change occur during the training is smaller than the specified tolerance limit. That is defined issue. Okay. So this one the Adeline training algorithm. So just I'm repeating this. So initially, at step 1, we are initialize the weight bias at learning rate. Then we should check the stopping condition, and if stopping condition has been not satisfied, then we should calculate the calculated output by using the formula b plus summation xi omega wi. Then we should apply the activation function, and after that we should compare the calculated output, the target output, and if the targeted output and calculated output are not same, weight updation will be take place according to the delta learning rule, and this iteration will be continued for the all input output patterns, and until the tolerance limit has been reached. So that is the basic Adeline Adeline learning algorithm, and this is basically the flowchart of the Adeline learning algorithm. So this one is the let's start. So at start we this portion is basically Heiji. So here this is just written here. Initialize the value of weight and bias and alpha. Next we should define the or specify the tolerance limit of error. Then for each value of s, that means for each of the input pattern, we can activate the each of the input units xi equal to si. Then we should calculate the net input. Then we should use the weight updation formula and calculate the error ei equal to here you are using LM mean squared error, but you cannot use, or you can also use last t minus y, and also and if uh, okay. So here you can see that if the tolerance limit has been reached, then we should stop, but if the tolerance limit has not been reached, then again the formula has been or the iteration should be continued. Okay. Now coming to the next topic, that is the multiple adaptive linear neuron, or Madeline. So you can easily interpret that Madeline, that multiple adaptive linear, that means many number of Adelines are connected in the parallel for this Madeline type of architecture. But for the simple case, we are considering only adaptive one adaptive layer. That what is the adaptive layer, that will be discussed in the next slide. And it should be keep in mind that in here we are considering only single output unit, and some important feature of the Madeline are given as followed. that the Madeline architecture is quite similar to the multi-layer perceptron. That means multi-layer. That means there should be some kind of hidden layer in between input layer and output layer. So it is quite similar approach to the multi-layer perceptron. And here Adeline will act as the hidden layer in or hidden unit between input and output of the Madeline. And it should be keep in mind that weight and bias between the input and Adeline layer can be adjustable, whereas the weight and bias in between Adeline and output layer are fixed, and those value are basically the one, and training can be done with the help of delta rule. Now let's see. uh, yeah, this one is the basically the architecture of the Madeline model. So yeah, you can see that this one is the input layer, and this one is the input nodes. So there is n number of input neurons, x1 x2 up to xn. And y is the output node. We are considering here, we are considering the single output unit. So here there is only one neuron in the output layer. uh, okay. And you can see that in between input layer and output layer there is another extra layer which is called as the hidden layer in case of perceptron, but here we are using the term Adeline layer. Okay, so this one is the Adeline layer, as there is another Adeline layer in between input and output, so that's why you use the term multiple Adeline. Okay, so this one is the basically Adeline layer, and output layer is also called as the Madeline layer. So there should not be any confusion in between these uh, two term. Like the in the middle layer or hidden layer is also called as the Adeline layer, and the output layer is also called as the Madeline layer, and this one is the input layer. Okay, so x1 x2 xn are the input neuron, whereas the q1 q2 up to qm are the hidden layer. It should be keep in mind that the value of n and m are not same, or maybe same, but in general they may not be same. Okay, and each of the neuron from input layer is connected to the each of the neuron of the Adeline or hidden layer by using the defined weight. Okay, and also each of the node have some kind of bias. The default value of the bias is 1, but the weight of that bias can be adjustable. And you can see that after that the output of the each of the neuron in the hidden layer or Adeline layer is going to the Madeline layer or output node. Okay, so here so you can see that that means here there is some kind of accumulator and activation function, and after that at the Madeline layer there should be another kind of summation or accumulator and activation function also. So here there is one set of accumulator and activation function, and here another accumulator and activation function. Those are the quite similar different. Okay, and one another thing you should be keep in mind that the weight between input and Adeline are adjustable, whereas the weight between qn and output layer are not adjustable, and their default value is has been set to the 1. Okay, so we are trying to adjust only this value only. Okay, okay, fine. So let's continue, or let's start the training algorithm for the Madeline architecture. So the first three step are same. So we need to initialize the weight, bias and learning rate. After that we should define the stopping condition or stopping criteria. Okay, and next is the activate each of the input, like xi equal to si. So for I equal to 1 to n, and for each of the input at the for each of the input we should calculate the output for the each of the hidden layer. Okay, so here we are defining the output from q1 hidden node or hidden neuron as qinj. So it is nothing but bj plus summation from I to n xi into wij. Here you can see that this one basically w11, this one w12, like this, or this one w1m. Okay, so here that's why with the term wij. Okay, in the earlier cases where there is only Adeline architecture, we only use the term wi, but here we need to use the wij, because there is another hidden layer has been introduced in between input and output layer. So we are using the output qinj by using this formula. Next it should be going through the activation function of the hidden layer. So apply the following activation function to obtain the final output of the Adeline. Okay, so fx equal to 1 and -1 for x equal to greater than equal to 0 and x less than equal to 0 respectively. So output of the hidden unit, that will be qj, is nothing but function of qinj. So how can we get the qinj? So qinj is nothing but this, by using this equation, can be obtained. Okay, and the final output. Okay, so after that, after that, all this value, that means qj, sorry, qj, that like the output of this q1 is qj, and q2 q, like this way. So all these are moving towards the output node, and there is another accumulator. So in the output of that accumulator of the output layer will be q1 v1 plus q2 v2 plus qm vm, like this way, plus b0. Okay, so like this way you can write that output of the network of the Madeline layer uh, is yinj plus equal to b0 plus sorry, from j equal to 1 to m qj into vj. Here you can see that as the number of hidden neuron is m, so that's why the summation has been taken from 1 to up to m. Okay, so by using, after getting the yinj, it should be going to another activation function, and that will be output, will be ultimate output will be y equal to f y a I n. Okay, clear? So again I am telling, so for each of the input pattern x1 x2 xn, we should calculate the output of the hidden node. Okay, by using this formula, and we get q1 q2 q3, and q1 q2 q3 has reached to the output node by where there is weight of v1 v2 up to vm. So then we should get that value by using this equation, and after that it will again going through another activation function of the and ultimately we get the final output of the network y equal to fyn. Clear? Okay, now we can easily calculate the error. Okay, so here we should compare again the comparison, that means the feedback loop that has been remain in case of Adeline architecture. Here there is also another feedback loop, but for the simplicity of the architecture, the feedback loop has been not shown, but we should compare the calculated output with the target output, and if the value is target output is 1, then we should use this following formula: wij new equal to wij old plus alpha 1 minus q inj into xi. Okay, so here t equal to 1, that's why I use the term 1. Okay, but in case of delta rule, normally this one is the t minus respective output, t minus calculated output. So here calculated output is qinj, so we should use the term 1 minus qinj. And similarly, the bias can be updated bj old plus alpha into 1 minus qinj. Okay, so it should be remember that in this case the weight would be updated on qj, where the net input is close to 0 because t equal to 1. Okay, and another thing, it should be another case can be consider that when target value is not equal to sorry, calculated value, and the target value is -1, then obviously this will be just -1. So wij ik new equal to wik old plus alpha into -1 minus qink into xi, and similarly bias value is by old bias plus alpha -1 minus qink. Okay, and should we again keep in mind that the weight would be updated on qk, where the net input is positive because t equal to -1. Okay, so here y is the actual output and t the target output, and if the mm, y equal to t, no, there will be no update. Okay, and this process will be continued until the stopping criteria has been reached. So this one is a basically Madeline training algorithm. I hope there is no confusion, and if you have any problem, please post them. So coming to the conclusion part, so in this tutorial class we have discussed about the delta learning algorithm, where the weight has been adjusted by using difference between the target output and the calculated output. And delta learning algorithm has been implemented on Adeline and Madeline architecture. Adeline is similar to the perceptron but with extra feedback loop. And Madeline is the multiple number of Adeline are connected in the parallel way. Okay, in both cases, delta learning rule can be implemented. So like this way, neural network for the Madeline architecture can be trained by using delta learning rule. Okay, so these are the few references. Thank you. And if you have any question, again I'm telling you to post them on the YouTube video or the in the Google Classroom. Thank you.